Alright, the last thing we want to look at in Feynman diagrams is we want to look at an IB example. So we want to see where you would see this on an IB exam and in what context you would see this. So for this, we have silicon 30. It can be formed from phosphorus 30 by the process of a beta plus decay or a beta positive decay. So what we're starting out here with our parent element, we're starting out with phosphorus 30, and our daughter element's going to be silicon 30. Now they don't have to tell you the daughter element's silicon 30, we can certainly work that out. So we're told we're starting with phosphorus 30. So if you look on your periodic table, phosphorus is going to be element 15. And then yeah, we can deduce this is silicon 30, because we know in a beta negative decay, we certainly have to, or sorry, a beta positive decay or beta plus decay, we certainly have to have our positron, our 0, 1 beta. If you put 0, 1 e, that's fine. And we have our neutrino. And then we can look at our conservation laws to deduce the daughter element. So we know that the neutrino is not going to contribute to our nucleon number nor our charge number. So we know the particle that's left is going to have a nucleon number of 30, or an A value of 30, which we're told. So that's good. And then by deducing this, we know 1 plus 0 plus 14 is going to give us 15, so we're going to conserve charge. And then yeah, we know on our periodic table we're going to get silicon for our element. So that is our nuclear equation. So what you're going to be getting marks for on an IB exam, you're going to be getting marks for actually writing this correctly, as well as writing the beta positive particle and the neutrino correctly. That's what they're asked. That's what they're looking at. Now for this, it's asking you to sketch a Feynman diagram that represents this reaction. So the diagram has already been started for you. So what we're looking at here is we're looking at beta plus decay. So in beta plus decay, we have one of those U quarks is going to turn into that D quark plus that W plus boson, which itself is going to decay into the positron and the antineutrino. This is the example that we just did. But here's kind of what's happening here. So this is how this has started out. So we have our U quark and our D quark and our other U quark. So these first two quarks, these U and D quarks, we're just going to leave them as is. They're not changing. We're just going to send them on their merry way. So we got our U quark and our D quark. What we know this time, however, is that this U quark, that is going to be converted into a D quark. And then at this interaction vertex that we have here, we know for beta positive decay, we know that we're going to have a W plus boson. So we're going to sketch that W plus boson. And then that W plus boson itself at this interaction vertex, it is going to further decay into our positron and our antineutrino. So you'll notice they have time on the y-axis here. As I mentioned in a previous video, sometimes IB does that. We're used to doing time on the x-axis, so we might look at it like this. If we rotate it 90 degrees, not a big difference. So for our neutrino, it is a regular old particle. We're going to have the arrow going in the direction of time. And then for our positron, we're going to have the arrow flowing against the direction of time. So in an IB exam, this question's worth 3 marks. What are you getting the 3 marks for in this question? Okay, you're getting, first of all, you're getting a mark for showing that one of these U quarks converts to a D. You're getting a mark for that. You get a mark for showing that the actual mediating particle in this context is the W plus boson. And then the last thing you're getting a mark for is in this diagram, in this section here with the neutrino and the positron, you're getting a mark for showing the correct directions of the arrows. So the neutrino's arrow is going to point in the direction of time. The positron's arrow is going to point against the direction of time. So that's what you're getting your 3 marks from. And then the last one, and this is where I said sometimes they throw in that quark confinement. So it's talking about energies transferred to a hadron in an attempt to separate its quarks. So we're trying to put energy in to pull it, to basically separate the quarks by pulling them apart. So it's asking, well, what is happening in this situation, or explain quark confinement. Well, the first thing we want to talk about with that is what is quark confinement. So quark confinement means you cannot isolate particles. So quark confinement says, or sorry, you can't isolate particles. You cannot isolate quarks. Sorry about that. So you cannot isolate quarks. That's the first part. Or you could say, quarks can't be observed as free particles. They have to remain bound to other quarks. As long as you're saying words to this effect, that is okay. And the reason for this, we want to explain why this is. It's just because that the energy used to separate quarks goes into creating new quarks. So the energy going into separating quarks goes into creating new particles via new quarks. Creating new particles, quarks. So the big key on an IB exam, especially if it's a written question, not so much a calculation, but more of a written theory, take a look at how many marks it's worth. In this case, this question is worth 2 marks. What they're looking for is they're looking for 2 distinct points, because you're going to get a mark for each of these points. You're going to get a mark for basically telling what quark confinement is, and you're going to get another mark for explaining, well, what is happening in quark confinement. Well, when we put that energy in to separate them, we're actually creating new particles instead of separating quarks. And that's a big thing on IB exams for written theory questions. Check how many marks it's worth. Those are the number of distinct points they want you to say. It's not good enough to repeat the same thing twice. They have to be 2 distinct, separate ideas. But yeah, hopefully this kind of helps you out with Feynman diagrams. Hopefully it shows you where we actually see this in a more realistic IB context. In all honesty, for these type of diagrams for the decays, like the beta plus, beta negative decays, you're probably in your best bet to memorize them, but we always say don't memorize, know how you get these. That is always the best bet for this.